point. So what we had to do is we had to start with actually open foam in order to create our databases for the external electrode-based electrical field that we later on imported, inverted comma, imported into the PIC solver. Yeah? And we had to assess how is it with the required mass resolution and the particle weight variation. Yeah? Particle weight means you accumulate several or a large amount of charged particles in order to numerically reduce the total number of the particles in order to be able to cope with the theme from the point of view of the resources. But you cannot go to infinite values because at a certain point you get results that are not physical. Yeah? So this was analyzed and the outcome was that the weighting factor should be between 10 to the 5th and 5 times 10 to the 5th. And that we have to work with 19,700 something cells or more in order to get adequate results. For example, results that are not anymore dependent on the number of the grid cells. Yeah? This was one of the second or third steps. Then we looked at the charge deposition, and there are several methods. One is shape functioning, which means that your charges in the cell are smooth. Yeah? In order to cope with, you can say, inverted comma, the far away Coulomb interactions. So not the collisions, but the far away Coulomb interactions. And we learned from the results, namely the results in comparing the impact on the velocity distribution function, that this is not needed. So this was also a lesson learned. And then the last step was DSMC versus CMC. CMC is a continuous background gas Monte Carlo method that reduces the required resources that you need to simulate the neutral charge, neutral shocks, because we learned that we cannot cope with the problem by making use of our DSMC code, Las Vegas. What did we learn? We learned that CMC should be able to cope with the theme. This was also learned from the velocity distribution. So this was all preparatory work. Yeah? Nothing, no results. Yeah? Just learning how to implement. And then we did some work. Yeah? One was simulations with different densities without CMC, yeah, where we saw an electron check, which we will see later on. Then there was a fully symmetric simulation in order to have a verification activity. When you have the electrodes fully symmetric, you necessarily need not have to have a jet extracting. And when you simulate that and you find out that it works in that manner, then you have a verification. This was done. Then we did a simulation of the inner sphere region, where we learned that the simulation does not really follow the expectations, but we learned that this comes from the fact that this simulation does not see the external fields. Yeah? So the recommendation is that later on we should simulate the full IEC device instead of only a piece. Then simulation with CMC, which did not work out. As a matter of fact, we assessed the boundary conditions, but learned that at the whole, the boundary conditions from literature, from other co-workers, are too vague for this high fidelity assessment. So we continued with simulations with pure work on PIC. Yeah? And there we had two modes. We had a quasi-neutral inserting mode, where we inserted the plasma at the edge or at the inner region of the inner electrode quasi-neutrally, and in a second approach we violated the quasi-neutrality by keeping the ion density constant. Yeah, and the outcome of this simulation was nothing, 2 low Lorentz forces, and the outcome of this was electron jet extraction and a preemptive ion jet extraction. Okay, so this is the best. Now back to the roots. Let's look again at the simulation results for different densities or electron densities, where we saw actually in a preliminary step that we can visualize, and this example is shown here in the video, the electron jet extraction, which you see here. And this is for the first time ever that a jet extraction to any extent for an IEC has been simulated successfully. Yeah? But it's only the electrons. Yeah? In the next step, we looked at the ions, and the ions did not do that much. They were more or less homogeneously distributed with this, maybe for any reason that I don't know. And then over time, for different time steps, we see a certain movement of the ions, but the effect saturates. The effect saturates at a certain stage because of counteracting fields that are created by the ions that moved. So the whole thing stagnates. It doesn't move further. Okay? While if the situation here with the constant ion density, the situation looks different, better, but not that good. But very much better. How can you explain this? We see the evolution of the vectors, the velocity vectors of the ions, and you see the ions start from here and evolve into that direction until we get a saturation. Now, what is this? This is actually a result of the violation of the quasi-neutrality. So what happens is, we violate quasi-neutrality at the inner electrode by keeping the ion density constant, and the respective microfields that come from the Maxwell equation. So divergence E, I guess, is something like rho L over epsilon 0 maybe. Correct me if I'm wrong. Yeah? And these microfields are, from the point of view of the orders of magnitude, much more larger than the values that we get from the superposed fields from the electrodes. So apparently, they are the origin of the Lorentz forces that push the ions into this situation. But, as a matter of fact, we inserted the ions as a constant value, and by the time the ions move, with time, ion density at the origin reduces, and this again is the reason why the process saturates. However, we have a severe clue that within the acceleration processes, due to the fact that the electric field of the electrodes is fairly weak comparably, that this acceleration process maybe just not lives from, which theory says, from the fact that the ions are attracted by the electrons that move out, but that they may also live from the violation of quasi-neutrality, which we definitely have at the cathode. We have it. We have it at near surface situation of the cathode, but also inside. Because inside we have the ions catched. So a good result, and this concludes my executive summary. Yeah? So conclusion, we see the electron jet moving out on basis of the electric fields superposed by the electrodes rather than self-field effects, but they are still there. We cannot deny that these electrons may attract ions and attract them in a way that they move with, in a certain way, subject to inertia of course, with the electrons outside. But we see that the values that we get for the microelectrical fields due to the violation of the quasi-neutrality are a bit superior in a way, and most likely one of the origins of the acceleration process of the ions. Full stop. Thank you.